So today we will focus on the case of pick a number equal to 1. And before we enter into this part, there is one more interesting theory to continue since last time. Okay, so this is also a general property. Okay, so last time we talk about the property of the interamplified endomorphisms. There is one more thing I want to mention is due to the Professor Kawakami and Totaro about the bottle vanishing. Okay, so this is Kawakami and Totaro. I think it's published this year. Okay, it says that if X is a normal projective variety, such that it emits an interamplified endomorphism. So if this is an interamplified endomorphism of a normal projective variety, then this X satisfies bottle vanishing. So this is a very interesting application of from the viewpoints of the cohomology. So what's the meaning of bottle vanishing? So this means this X differential tensor with any ample divisor. Okay, so this is equal to 0 for any I greater than 0, J non-negative, and A is an ample divisor. Okay, for any ample divisor and any non-negative integer j and positive integer I, so this cohomology vanishing. Because this means when I write this bracket, it means the double dual. It's a reflexive Hall. Okay. Okay, there are several immediate consequences if we just consider X is smooth. Okay, and it is a Fano manifold. Okay, so the particular case is. So so when X is a Fano manifold, okay, so in this case, then we can take this A to be the anti-canonical divisor. So we can take this A to be minus Kx. Okay, then what can we get? So we can get this Hi X omega X. So now there is no bracket. It's just the usual exterior power. Okay. And then in this case, by using this perfect pairing, we obtain this is the n minus j. So if I use n is equal to dimension x, okay, then this equal to 0. Okay. So this Tx means it's tangent bundle. It's the dual of the the shift, the differential shift. Yeah, and also whenever we take this j to be n minus 1 and I equal to 1, then this means this h1x Tx equal to 0. So this means x is locally rigid. So basically, the locally rigid means if you have a deformation family of this Fano manifold X, so that the central fiber is just X, and around a small open neighborhood, every fiber has to be X. Okay, so this is the meaning of local rigidity. Okay, so this is some other useful application of interamplified endomorphism. Okay, so the last thing I want to summarize is, so if we start from this interamplified endomorphism, okay, F, then we obtain that by this theorem, it satisfies bottle vanishing. Okay, on the other hand, so for the convenience, we focus on the rationally connected variety. Okay, so rationally connected plus rationally connected. Okay, so by Yoshikawa, as I mentioned last time, it's of Fano type. And recall that what our final purpose is to try to prove, actually this variety has to be toric. Okay. And note that toric variety always satisfies bottle vanishing. So this is due to a result of Fujino.
And also toric variety, surely it is of final type. Okay. But there exists an explicit example which satisfies both vanishing but non-toric. So for example, if you consider this quintic diapason surface of degree 5, then it is not toric, but it satisfies both vanishing. Okay. Okay, now this is all the thing I would like to say for the lecture 1. So now we enter into the second part of our lecture. So first, it's about the introduction and our main results. Okay. So we recall this conjecture, which I called this endomorphism Pn conjecture. It says that if X is a final manifold of Pk number 1, so that it emits a non-isomorphic surjective endomorphism, okay, so the degree f is greater than or equal to 2, then X has to be the projective space. This n is the dimension. Okay, so before I introduce our main results, let us recall some previous results. Okay, some known results. So first is about the almost homogeneous space. Almost homogeneous variety. Okay, so this is due to two groups. One is the Paranjab Srinivas in 1989. Okay, so they solved the case of homogeneous manifold. Okay, and later on, maybe 20 years later, it's solved by Junmu Huang and Nakayama for the almost homogeneous variety. Okay. And the second case, known case, is about the hypersurface case. Okay, so this is known for hypersurface of dimension greater than or equal to 3. Okay, so this is also due to this for the quadric hypersurface case is due to the work of Paranjab and Srinivas, and for the degree greater than or equal to 3, it's due to the Bouvier in 2001. Okay. Note that for the hypersurface of dimension 2, there exists such the non-isomorphic endomorphism. Because if you consider the quadric surface in P3, then it is isomorphic to P1 cross P1. Then surely it has interesting endomorphisms. But if the Pk number is 1, that is, if the dimension is greater than or equal to 3, then even for quadric hypersurface, it admits no endomorphism. Okay.
Oh, sorry, by the way. Okay. L is over C.
Yes, and I think it's for at least for algebraic closed field of characteristic 0. But actually, such results can be extended to positive characteristics by another proof due to Kawakami and Totaro. Yeah.
The problem is Pk1 is much less restrictive or non-closed fields, right?
So yes. Okay. And if we don't consider this specific situation, for example, if we consider the dimension, then this is known up to dimension 3. Okay. So this is due to America, Rowinsky, and Van der Ven in 1999, I think. Yeah. Yeah, for this proof, they carefully used this rational curve theory in the final threefold. Okay. And also, some general statement in arbitrary dimension is due to Junmu Huang and Nagami Mok. So if there exists a rational curve, okay, so this is a rational curve whose whose normal bundle is trivial. Okay. This is trivial. I'm sorry. Okay. So suppose there exists such a rational curve whose normal bundle is trivial, then this conjecture is also true. Okay, so this is due to Huang and Mock in 2003. And in particular, the fourth result gives an alternative proof to the Professor America, Rowinsky, and Van der Waals result, because for final threefold of Picard number 1, except for this projective space and a quadratic hypersurface, any final threefold of Picard number 1 contains a rational curve with trivial normal bundle. Okay, so this result gives an alternative proof of this dimension, the final threefold case. Okay, finally, it's a very minor result. It's due to myself and Feng Shao. So this is if we consider this final index is no more than dimension minus 2, because in this case we have the good classification. So if you check case by case, then you can see this conjecture also holds. Okay, so this is due to Shao and also myself a few years ago. Okay. Okay, so now let me introduce our main result. It's also a joint work with Feng Shao. It's also published this year. Okay, the assumption of our theorem is a bit technical, and there are two assumptions. I want to carefully explain this later on, but first of all, let me write down the assumption. Okay, so we consider two final manifolds of Picard number 1. So let X and Y be final manifolds of Picard number 1. Okay, so this is, then we want to understand the finite morphism between X and Y. Okay. So there are two assumptions. So first, if the variety of minimal rational tangents, I use this VMRT to represent this notion. I will explain this later. So this is short for variety of minimal rational tangents. Okay, VMRT, variety of minimal rational tangents. So there are two. So this is a subvariety for this. So for each point x, if this tangent space Txx, if we consider it's the projectivization of hyperplanes contained in this vector space, then we obtain a projective space. Okay, and then this VMRT is a subvariety defined inside for each general point. So this x is a general point of x. Okay, then we can associate this point with a variety inside this tangent space. Okay, and also this Cy, we can also define this Tyy. Okay. Yeah, I will write the full name later, but for the organization here, I cannot write. So this is a variety of minimal rational tangents. Okay, I will explain what's the meaning of minimal rational curves later. Okay, so this is both of them are not dual defective. So this means that the dual variety of these Cx and Cy are hypersurface in its P of the cotangent bundle. Okay, because for every variety with this embedding to some projective space, we can always consider its dual variety. Okay, so this not dual defective means its dual variety is a hypersurface in the dual projective space. Okay, so
for each point x and y.
For a general point. Yes. Actually, this VMRT notion is well behaved only for general points. Okay. Yeah, I will explain this later. Okay, the second assumption is the tangent bundle. The tangent bundle Tx is big. So this means if we consider the Grothendieck projectivization of the tangent bundle, then the tautological line bundle is big. Okay? Then the conclusion is then any surjective morphism from X to Y is an isomorphism. Unless Y is projective space. Okay? So this means if these two assumptions are satisfied, then any surjective morphism between X and Y has to be an isomorphism, unless this Y is projective space. So for Y is projective space, surely this is true, because for any smooth project or for any normal projective variety, by the normalization theory, it always admits a finite morphism to projective space. So if the base is not projective space, then this means any finite morphism between them should be isomorphism. So in particular, it implies this conjecture when this VMRT of X is not dual defective and X has big tangent bundle. Okay? And later on, I would like to use this theorem to further develop under the dynamical assumption F, whether we can obtain some positivity of X, so that we can use this theorem to solve this conjecture.
If you said in your theorem that if tangent bundle of X is big, then any surjective morphism from X to any
To Y, X and Y are given.
Such that the car rank is equal to 1.
Yes.
So I mean that the first
Yeah, first
speaking about
some restriction on the final manifolds.
it's
So you have two final manifolds, X and Y,
yes.
and assume that for general points, the VMRT is not dual defective. Then, and further, if the source has big tangent bundle, then it has to be an isomorphism. Okay? Yeah, I'm sorry, because these two assumptions are not very easy to explain, but I will try to explain this clearly later. Okay? Okay, so I will give some remark. So there is a famous theorem due to Jim Huang and Nagami Mok in 1999. So their theorem says that if X is rational homogeneous of Picard number 1, then any surjective morphism from X to Y to a smooth projective variety.
X is rational.
Homogeneous. Yeah. Yeah. To a smooth projective variety is an isomorphism. Unless Y is projective space. Okay? And why I want to mention this theorem, because if the variety is rational homogeneous, then its tangent bundle is always nef and big. Okay? So somehow our theorem is to try to extend their theorems. Because if we can remove the first assumption for this VMRT assumption, then this theorem says that for any final manifold of Picard number 1 whose tangent bundle is big, then any surjective morphism onto another final manifold of Picard number 1 has to be an isomorphism, unless the base is projective space. But yeah, I will explain later that actually the first assumption is quite mild, because for most of the varieties, this star assumption is satisfied. For example, if you consider hypersurface or consider complete intersections, so such assumption is automatically satisfied. Okay, so the second remark is, if X is rational homogeneous, then its tangent bundle is nef and big. Okay, so this is this is follows from the Springer map. Okay, use some differential geometry. Okay, our theorem B is not very technical, so it's more easy to explain. Okay, let me explain another theorem. Maybe it's due to myself. Yeah. Okay, if we consider an interamplified endomorphism, so if this is an interamplified endomorphism, such that this X is smooth rationally connected, okay, then its tangent bundle is pseudo-effective. So this pseudo-effective means there are two, so this is slightly stronger than the usual pseudo-effectivity. So this means this PTX, the tautological line bundle is pseudo-effective, plus its restriction base locus, okay, that's not dominant X. Okay, so this pi is a projection from the Grothendieck projectivization of tangent bundle to X. Okay, so this means, except for this tautological line bundle is pseudo-effective, we also require this the bad locus of the restricted base locus does not dominate the whole X. Okay.
So I don't understand the last.
Sorry.
The last string. What does it mean?
So this means if you add a, okay, so this is defined by the union of the, so for example, this n equal to 1 to infinity, and you fix
What does B?
base locus.
Okay.
Yeah, this means if you consider the stable base locus of this O1, you add some very small ample divisor, all the base locus, you take the union. So this is the definition for the restricted base locus. Okay, so this means its restricted base locus cannot dominate the whole X. Okay, so let us compare this theorem B and theorem A. So for theorem A, we assume the tangent bundle is big. Then we somehow obtain this positive answer for this conjecture. But when this, why we need to assume this assumption 2? So initially it's a very strong assumption. But what I would like to say is, if we assume this dynamical assumption, the existence of this endomorphism, indeed we can really obtain some positivity for this tangent bundle. Okay? Although there is still far away from this pseudo-effectivity to the bigness, because bigness lies in the interior of the pseudo-effective cone. But at least we obtain the first step towards this expectation. Okay, we want to show this tangent bundle is big, but at least we can show it is pseudo-effective. Okay, and then starting from pseudo-effective, we can also have some other approach to consider this problem. Okay. Okay. So any questions so far? Okay. Let us enter into the second part, which I would like to briefly introduce this theory of minimum rational curve. Okay. So this theory is initially independent of the dynamical assumption. This is a very well-developed theory to study the final manifolds. Okay. So it's more a complex geometry and a differential geometry. So we're starting from a smooth projective variety. Okay, I use X to represent this smooth projective variety. Okay, I use the notion of rational curves. Okay, I use this notion to denote the normalization. Okay, this N represents the normalization. Okay, normalization of the open subset of the Cho variety. Okay, so the element in the Cho varieties represents the subvariety. Okay, we regard this subvariety as a point in this space. Okay, to denote the normalization of the open set, what's this set? Okay, parametrizing. Integral rational curves. So this meaning is, so inside this Cho variety, we take all of the elements which represent the integral rational curves. Okay, so this form an open set. And then we take the normalization to denote this as the rational curves. Okay, I use this notation. Okay. And then we can discuss the components in these rational curves, the parametrizing space. Okay, so a dominating family I use K of minimal rational curves. Okay, so I will explain the meaning. What's the meaning of dominating family of minimal rational curves? Okay, so this is an irreducible component of this notion, IT curves. Okay, but this is not enough. So the dominating, what's the meaning? So this means all of the elements inside this component should cover this X. Okay, dominating means, yeah, all of the elements, if you take those rational curves, then such family should cover this X. Okay, so this means such that, so the locus of this K. So what's the meaning of locus of K? So the locus of K means for every element in this K, it represents a rational curve. And you collect all of those rational curves in this X, then it should be dense in X. Okay? So this swept out by curves from K, this is dense in X. Okay? So this is the meaning of dominating. And also we need to assume another assumption for the general X. Okay, so if we take a general element, general, okay, then this Kx. So what's the meaning of Kx? Kx means we consider all the elements in K which passing through this point X. Okay, so let me draw a picture. So this is our X, and we pick a general point X, small x. Okay, and then we collect all of the elements lies in the family of K. So this means there are several rational curves passing through this point. Okay, okay, okay. Sorry. Rational, yes, rational curves, because this component is taken from this rational curves component. Okay, so we collect all of those red curves, then it forms a subset, a subvariety of K. Okay, so I use this notion Kx to represent all of the curves in K passing through the point X. Okay, so this is proper. Okay. It's proper in K. Yes. It's a subvariety. Yes. Later on, you can. Oh, yeah.
I just lost. I'm sorry. Can you repeat the thoughts?
You want so for these two assumptions.
What was the assumption?
Okay, the assumption. So for a family K to be dominating family of minimal rational curves, so note that there are two important notions. One is the dominating. The second thing is minimal. Okay, so dominating means the locus of K. So what's the meaning of locus of K? This means, so K is a component of the rational the parametrizing space of rational curves. And if we collect all the elements inside this K, then it should cover the whole X. Okay? So somehow we can imagine this as some universal family, and this is K.
Yeah.
And then it's the evaluation of X,
Yeah.
and this has to be dominant.
Yeah.
Okay? So this is the meaning for the dominating. And the second thing is minimal. Okay? So minimal corresponding to the subvariety of Kx is proper. So Kx means, so generally speaking, Kx, you can imagine this as you take a point X and you take the inverse image and its image here. Okay? So, but simply speaking, if we take some general X, this Kx corresponding to all the elements in the parameterized space which passing through the given point X. Okay.
Why should be any point of X? Or it's
Oh no, general, only general. Yeah, general. Yeah, I have said general.
The difference of the dimension is kind of incomparable with rational connectedness, right?
Yes. But later it's a well-known theorem that for any uniruled projective manifold, it always carries such a family. Yeah, yes.
From
Yeah.
uniruled to-
Yeah, for uniruled variety, not necessarily rationally connected. Yeah, but it's more interesting. This case is more interesting if the manifold is rationally connected. Okay. Okay, let's continue. So this is what I would like to say. So any projective manifold, uniruled, it always carries a dominating family of minimal rational curve. Okay. So this is proved by, I think it's a classical result, but if you want to find a reference, you can check the Junmu Huang's lectures. Okay, he gives some proofs using the differential geometry. Okay.
what?
Sorry? Uniruled carries, there exists such a dominating family of minimal rational. Yeah. Okay, let's continue. 5. So in the following, I always use this K to represent a dominating family of minimal rational curve. Okay? So for a general element, this general element, this L in the family K, it should satisfy a very good property. Okay. So what does it satisfy? We call it standard. Okay. So this general element is standard. In which sense? In the sense that if we take the normalization of this L, so note that this L is just an integral element. It may not be smooth, but if you take the normalization, it has to be a smooth rational curve. Okay, I use some mu to represent its normalization. So if we consider this tangent bundle restriction to this L and then pullback to P1, so I use this mu pullback Tx. Okay, so this basically means if this L is smooth, then you just restriction to this of the tangent bundle to this curve. So by the Grothendieck Grothendieck splitting theorem, surely it is a splitting bundle on this P1. Okay, so but for this general element in this minimal rational curve, okay, note that this is minimal. This minimality is used here in. Okay, so it has a very nice decomposition. So this is P1, 2. So this is the part basically it represents this TL. Okay, because for a smooth rational curve, its tangent bundle is just O2, right? And plus some OP1, 1, there exists some P and direct sum with some other summand with trivial. So this is n minus 1 minus P. Okay, so what's the meaning? So because this X is of dimension n, so its tangent bundle has rank n. And then if you restriction to a subvariety, the rank is still n. Okay, so basically this means if you choose a general element in this component K, then there are 3 segments. So the first part is this O2. So this O2 represents this TL. Okay, the second part is this O1 plus some P. I don't know this P, what is this P, but this P is some non-negative integer. And finally, there are some trivial segment. Okay, so if you restricted this Tx to a general minimal rational curve, to a standard minimal rational curve, then actually it's NAF. Okay, there is no non-negative segment, and also it's the minimal. So this is the minimality means. So if you take the non-minimal curve, then this part could be higher, could be larger. But this form, as we can see, it's the minimum situation for the NAFness which can happen. Okay, so I would like to explain this in this way. Okay, and also if we consider the other.
Is it possible to write P in some sense? Is it possible no L and this mu to write P exactly? Or?
Yes, if L is smooth,
yeah. Then
this mu is identity.
Ah.
Yeah. This mu means the normalization, because L is just the integral curve. Okay. So from this standard sequence.
This is the definition of a minimal rational curve.
Yes. All of those definitions are equivalent, but I just want to give a full explanation. Okay. So if you feel this is too technical, then you can forget this. You just remember a standard rational curve has to be in this form. Okay. And every projective manifold, every uniruled projective manifold always has such a minimal rational curve. Okay. And I can give you another way to understanding this sequence. So if you just consider the usual normal bundle sequence, right? So this is the tangent bundle, the restriction of tangent bundle, and this is the normal bundle. Okay, so this is the standard sequence if we assume L is smooth. Then you can find, actually this part, as I mentioned, is TL. And this part corresponding to its normal bundle. Okay? Somehow this splits. Yeah. There are two parts. One is from TL, the other is the trivial is the normal bundle. Okay, this part has rank n-1. Okay? Okay, now let us continue. And also you can by using this basic deformation theory, actually you can calculate this dimension of K or dimension of Kx in terms of this sequence, in terms of P. Okay, actually this dimension of K, if you check this book of Cola by these rational curves on varieties, yeah, there are some very explicit formula. So this dimension K is actually equal to dimension X minus Kx times L minus 3, which is dimension X plus P minus 1. And this dimension Kx is exactly P. Okay, so this minus 3 means when we consider the deformation of rational curves, we need to minus the dimension of the automorphism, or the self-automorphism, because the dimension of the automorphism of this a smooth rational curve, it is 3-dimensional. So you need to minus this 3. And then this is just n, and this Kx times L follows immediately from this exact sequence, this splitting. And then you can use this P. Okay. And for this dimension of Kx, it's also not very hard to prove. Actually, this dimension coincides with this P. Okay. Okay, next. So in the following, we fix a general point X, which is general. And then we take the normalization of Kx. So although this Kx is a variety, but it may not be normal. It may not be normal.
I just have a
Sure.
What is Kx?
Oh, Kx means you take all of the elements in K which passing through this point X.
Okay.
Yes. Okay. Yeah. Okay, there is another way to understand this k and kx. For example, as I said, if you consider this universal family, and you consider k, and you consider x, and then, using this dimension k equal to dimension x plus p minus 1, then this fiber, note that this is a P1 bundle. Because this is a parameterizing space, and it's a universal family for every element, it corresponding to P1 for general element. So this is 1 plus this dimension. So the dimension U is dimension x plus p. Okay, dimension x plus p. And then this, the dimension of this fiber of the evaluation is actually equal to p. Okay.
It should be obvious that this p is the same as the times we add up
kx.
1.
Sorry?
It should be obvious that this p and
Yeah, coincides with this p.
And should it be obvious or is it trivial?
It's corresponding to the, we need to use some cohomology of the tx. Yeah, it's not directly,
Okay.
follows. But if we check this book due to Cola, then there are some explicit formula. Okay, let's continue. So if we fix the general point x, then we take the normalization of this kx. Okay, I use this as a normalization. Okay, and then this is a finite union. Actually, this is a finite union of smooth projective variety of dimension n, of dimension p. So why this is true? Because we take a very general point. We take a general point x, so that this kx actually has a good condition. And then after taking normalization, there are several pieces, okay? And they are the smooth projective variety of dimension p. Okay, okay, now I will define the meaning of VMRT. I'm sorry, this is a long story, but this theory is well developed until maybe 20 years ago due to Junmu Huang and Nagami Mok. Yeah, this is a long story. But actually, this theory is very useful to if we study the final manifolds. Okay. So till now, we have already known this notion of kx. Okay. Then what we should do? Okay. So let us consider the tangent map. Now this everything is more geometric. Okay. Let us consider the tangent map. So what's the meaning of tangent map? We define this tau x.
So and usually the general fiber is singular. Yeah.
Which general fiber?
This kx.
No. If x is general, then kx is smooth. Yes.
So we fix the general and then we take normalization.
Yeah, but yeah. My meaning is, it may be several pieces of smooth projective varieties, and after we taking the normalization, they are resolved. I mean, they becomes finite union. Okay, and then this is a finite union of smooth projective varieties. Okay, so what's this tangent map? So we define this to be omega xx. Okay. So we take a general element L. So L is a general element in this kx which passing through x. Okay, so this means, so we have an element. So this is L. Okay, and this is our x. Okay, then what's the meaning? We sending this element to the tangent direction of this rational curve. Okay, so we send this to the tangent direction of L at x. But note that this notion may be confusing because for the tangent space it should be txx. But note that now this is in the sense of hyperplane. Okay, so I use the dual notion. So if you consider the projectivization of the usual projectivization of lines, then you should write ptxx. But here, I use this notion because I use the Grothendieck notion. Okay, so basically it means you collect, you send this point, the tangent direction of this L at x. Okay, so let me, so, okay, so this is the tangent direction. So this map means for every L, okay, so this is one L. So suppose you have another point, you have another element passing through x, for example, if you consider another L, so this is the L, this is L prime. L and L prime are all lying in this kx. And there is another L, means it passing through x and it contributes to another tangent direction. So for this L prime, it can send it to this direction. Okay, so this means for general L passing through x, you can give assign it a tangent direction, okay, as an element.
Maybe we should take dual.
Yes. I have said if you only consider the usual projectivization of lines, then you should write this as PTXX. But now, all of the projectivization in our case is in the sense of Grothendieck. Okay, so I use this dual version. Because for this tangent direction, this is a line in the vector space, right? And then if you consider its projectivization of lines, it should be an element in the usual projectivization. But I use the Grothendieck notion, so I use the omega xx. So is there any confusion for this notation?
So when you define the projectivization of a bundle, you define it as a approach scheme of an algebra that is a direct.
Yes. It's the sense of Grothendieck.
Not the dual.
Symmetric. Yes. So if you consider just the usual projectivization of lines, then here it should be read as PTXX. Okay. Because sometimes it's a bit confusing, because in our case, we also use some positivity notion, but all of them are in the sense of Grothendieck, so I don't want to introduce some different definitions which make us more confusing. Okay, then now this Cx. Okay, so this is the Via-Marti. Okay, so this Cx is defined to be the image of tau x. Okay, so this is our Via-Marti. So you can imagine the meaning variety of minimal rational tangents. It's actually gives a very clear notion for this definition, because minimal rational tangents means the tangent direction of every minimal rational curve. Okay, so we collect all of those tangent directions together to obtain this Via-Marti. Yes.
What does it mean that they are not dual?
Defective. I will explain this. Okay, and then indeed more can be said for this tangent map tau x. Okay, indeed it follows from the big theorem of Capecius and Huang-Mock. So by Capecius in 2002 and Huang and Mock in 2004. So actually this tau x is the normalization map. Oh, sorry, here I should use kxn. Okay. So actually Capecius proved this tau x indeed is a finite morphism. And Huang and Jun Huang and Nagami Mock, they proved this tau x is birational. So it's a finite birational morphism from a smooth projective variety. So this is the normalization. Okay. So and also you can check this dimension, because this is the normalization onto the image. So this dimension of this Via-Marti coincides with the dimension of this kx, which is p. Okay. So let me give the full notion. So we call this Cx. We call this Cx as the variety variety of minimal rational tangents along X. Okay, so the story is every time if you consider a general point in a final manifold, then you consider the component of minimal rational curves, and then for each minimal rational curve passing through this point, there is a tangent direction, and you collect all of those tangent direction together, you will obtain this VMRT.
Can I have a silly question?
So,
So if there we got omega, then why on the right board we got t?
T?
Like here, this map, its base is omega.
Right.
And the same, yeah.
At the condition start, VMRT is contained in where? On the rightmost blackboard, yeah, lower.
Thank you very much. Yes. This is not true. It's not true. I'm sorry for the confusion. Yeah. You are right. Now I myself get confused. Okay, this should be omega. I'm sorry. Yes. Actually, for this txx, this is the dual variety lies in the txx. Okay. So this not dual defective means. So this means.
What does mean rational tangent?
Sorry.
What does mean rational tangent?
I explained this because this kx is all the minimal rational curves passing through x, and you take for each rational curve, for each minimal rational curve, you take its tangent direction, and you collect all of the tangent direction together, you obtain a variety. So this is called the variety of minimal rational tangents. Actually, it should be the tangents of minimal rational curves, but it's too long, so we just use this variety of minimal rational tangents. Okay, VMRT. Okay, thank you for the correction.
MRT doesn't depend on the choice of k.
Indeed, it really depends. But if we consider a final manifold of Picard number 1, there is a unique such component. Yes. So usually we need to first obtain minimal rational components k, and with respect to this k, we can discuss this VMRT. But for the final manifold of Picard number 1, this k actually is usually intrinsically defined. Yes. So for example, if you consider the conic bundle structure for the very easy example, if we consider P1 cross P1, then there are two components. There are two projections. And actually, for each projection, for each fiber, it has trivial normal bundle. And actually, they are minimal rational curves. So there are two different components, two different k. This is k1 and k2. And then, in this case, we need to specify which k we are talking about. But for final manifold of Picard number 1, this is automatically, yes. Okay, so the definition for this VMRT being non-dual defective means, so this means if and only if the dual variety of Cx, I use this check. Okay, it means the dual variety. Okay, so the dual variety lies in this PTXX. Now I use PTXX. This is a hypersurface. Okay. So the dual variety basically means we consider all the hyperplane tangents to this variety and collect all of them. Yeah. So this is the so maybe I can give a rigorous definition later.
It's definition of not dual defective or dual defective.
It's definition of dual variety, yes.
Not dual defective.
Not dual.
So dual defective means it's not a hypersurface, it's of a high codimension. Okay. So as I mentioned, for most of cases, for example, if this Cx is a complete section in the variety, then its dual variety is always a hypersurface. Okay, there are only a very few situations for which the dual variety is not a hypersurface. Okay. Yeah. For otherwise, But if you just consider the degree, not linear case, we need to fix the minimum embedding. Yeah. For otherwise, yes, you are right. For example, if you just consider line in P2 or P3, then surely it's still is it's not a hypersurface. Right. You are right. Yes. But actually, this theorem not trivially, this theorem holds true if the VMRT is linear. This is also proved by Junmu Huang and Nakayama, I think. Yeah. Okay. So let me check how much time I left.
Half an hour.
Okay. Thank you. So now everything is defined inside this omega x. In the following, because we need to relate this theorem to our positivity of tangent bundle, so now we would like to go to the dual variety to live in the PTX. Okay, so this is what we would like to say. Okay, so for a standard rational curve L in K, we define the meaning of minimum section. I use this L bar to live in the PTX. So this is given by the surjection. Okay, so let me explain this. No, TX. Because why? No. So now I have said we need to consider PTX to X. Right? So for every minimum rational curve living here, we would like to define some section dominating this curve. So this is called the minimum section. And to define a subvariety living in this PTX, it's equivalent to define the quotient. To define the quotient, because it's by the Grothendieck this corresponding. So every quotient, every surjection, actually. So for simplicity, I remove this mu. Okay. So we just consider smooth rational curve because general element. Okay. We just consider this Tx restriction to L. So there is a L living here, and we consider this restriction. The inverse image of this L inside this PTX. It's also a Pn-1 bundle over this curve L. And we would like to find some minimal section, minimal curve living here. To find some subvariety in the projective bundle, it's equivalent to find the surjective quotient, right? Okay, then why there exists? So as I mentioned, this actually, what's this? Recall that this is O2 plus O1 plus P plus O n minus 1 minus P, right? So this means once this is non-zero, if it is non-zero, there always exists the natural quotient, right? So, but when we do not have this situation, so this means if n minus 1 minus p is 0, then what happens? So if n minus 1 minus p is 0, this means there does not exist such a summand. Then we can find this minus kx times L. This is, what's this? This is just a p plus 2, right? And since if this is does not vanishing, this vanishing, so this is 0, then p is equal to n minus 1. So this is equal to n plus 1. What does it mean? Yeah, when we do not have such a quotient, then this is 0 and this is n plus 1. But then this, what does it mean? So you find some curves, some rational curve with intersection with the anti-canonical divisor equal to n plus 1, then this has to be projective space. Okay, so for any non-projective space, this final manifold, there always exists such non-trivial summand, so that you can always find the minimal section. Okay, only when this variety is projective space, then it has to be ample. Then you cannot find the trivial quotient, because ample vector bundle, the quotient is always ample. But in all of other cases, you can always find this OL. Okay. Okay, then for each quotient, you obtain a minimal section L bar living above this L. Okay. And also note that it satisfies such an assumption equal to 0. Okay, this eta is just 0, 1. Okay, why? Because this follows immediately from the definition. Okay, this tautological line bundle restriction to here, it has to be 0. Okay, this L bar. Now, with this minimal section defined, we can define this so-called the total dual VMRT.
What is eta again?
Eta is the tautological line bundle 0, 1. Because this L bar is defined by this quotient. Yeah, then it has to be 0, okay? So now we define this so-called the total dual VMRT. So this VMRT is living in the P omega x. So the total dual VMRT, you can imagine it lives in the PTX. And what's this total dual VMRT? Actually, we just collect all of this L bar. Whenever this L runs through the minimal rational curves on X, we collect all of this L bar together to obtain this. So this, I use this C check. Okay? So this C check is equal to the union of general L in K and this L bar, and take its Zariski closure inside this PTX. Is it clear? Okay, so for every minimal rational curve in X, we find some minimal section, and we collect all of these minimal sections together, and they are all living in PTX. And we take the Zariski closure. Okay, we take the Zariski closure. Then what happens if this C, what happens if this C is not dual defective? You can find actually this C hat has to be this C check has to be a divisor. This is actually a divisor, a codimension 1 subvariety. So that this is more, it's very useful for us in the analysis of this projectivization of tangent bundle in the Cone analysis. Yes. Okay, anyway, I first define this. I will explain.
It's very general definition, right? It's like a projective dual, right?
Yes. But a priori is for every, so this C check, we know this C check 2x, this is dominant. Because why? Because so the minimal rational curve covers X. And for every minimal rational curve, you can find the minimal section. So that this collection of all of the minimal section has to dominate this X. Okay. But a priori is why this C check X is the dual variety of Cx. I didn't prove this actually. Because for Cx it's defined just by taking the tangent direction. But this C check X is defined by the minimal section. Why they are the dual? So this is due to a very important proposition. Okay. So the proposition due to Monius. Is it pronounced correctly? I'm sorry, sometimes, my Monius. Okay. Ocheta, Conde, Watanabe, and Wisniewski. Okay. So they proved what? What they proved? They proved that this Cx check is the dual of Cx. Okay, so what's the definition of this C check X? So now we have this C check, which is a irreducible projective variety, dominant X. And for each element living in X, we take its fiber. Okay, so this is the definition of the Cx check. And actually, it's the dual variety of Cx. Okay, because you can see this Cx check living in the PTXX, and Cx itself living in the P omega XX. So it's the dual variety. Okay. And hence, if this Cx is not dual defective, this means Cx check, it is a hypersurface. Okay, so for general element, this fiber is a hypersurface. So this means this C check itself is a prime divisor inside this PTX. Okay? Okay, now, maybe I'll remove this part. Okay, we have another theorem. Well, this is due to also Shao and myself. We use some symplectic geometry and foliation theory, but I will not introduce here. What we proved is, so suppose we still have this assumption. Okay, so for this x to y. So for any surjective endomorphism from x to y, there is an induced rational map from ptx to pty, right? Maybe I will give some explanation this later on. So I use this f prime. Okay, this is the induced map. Okay, suppose this f tilde sends the total due of MRT to the total due of MRT. Then we obtain this f is an isomorphism. Okay, so what's this meaning? So this means now we have defined the total due of MRT inside this PTX as a prime divisor, right? So this theorem says that, so for final manifolds x and y, we have their corresponding dominating family of minimal rational curves. And for each dominating family of minimal rational curve, we can define its total due of MRT. So there are two total due of MRT inside the PTX and the PTY. Okay, for each x and each y, we can define its total due of MRT. And suppose this induced dominant rational map sends, or maybe this is f prime. Oh, sorry. So suppose this f prime sends the total due of MRT of this x to the total due of MRT of y, then actually it has to be an isomorphism. Okay, so later on, to prove our theorem A, we are left to check whether the induced rational map sends the total due of MRT to the total due of MRT. Okay, using this theorem C. But this theorem C actually needs some other proofs, but I will not introduce here. Okay, so now in the remaining part, I will.
We don't ask them to be surjective or whatever.
This is the same assumption here. The surjective. And the final manifold of pk number 1.
So it's the same as the theorem.
Yes, with this similar assumption, yes. Yes.
I have a very silly question.
Sorry.
If we're dealing with bundles in the graphic sense, then why is the differential covariant?
Why you mean why there is a map?
Why is in this direction if we are dualizing everything in fact?
You mean it should be PTY to PTX or something like that?
Yeah.
Actually, this now let me write down how can we get this map. So we have x to y, right?
Yeah.
And we have PTY. Yeah. And we have the pullback action, the fiber product, PF pullback TY, right?
Yeah.
Okay, so we have the natural map from omega f pullback omega y to omega x. This is the injection, right? And then we have we're taking the dual. We have the 0 to tx to f pullback ty, right?
Yeah.
So away from some closed subset, this is an isomorphism.
But
then you can obtain this dominant rational map from here to PTX. This is birational. This is induced by the injection, as what I said.
Okay, maybe I should ask my question after the lecture, because it's a very long one.
Oh, okay. Okay, so this diagram, so that we obtain this. This is the birational. Okay, so we obtain PTX to PTY as a dominant rational map. Because we have 0 to f pullback omega y to omega x. This is the standard project. And you take the dual, you obtain tx to f pullback ty, right? And this is also a generic isomorphism.
Yes.
And because this is locally free, the generically isomorphism, so it cannot have, its kernel is also torsion free, but it cannot have positive rank, so it has to be 0. So it's also injection. And for this injection, this means it's also generic surjective, so it's generic isomorphism. So over the over the open set, they are isomorphism, so you can always construct this rational map, okay? Birational, actually. Okay, so now let me give you some explanation. Now this everything should be more easier to explain, yeah. So now in the following we will assume C, okay? Assume C. Assume theorem C. Let us prove theorem A. So then what should we prove? We should prove when Tx is big, then we obtain this dx is sent to dy. Dx is sent to dy. So in the following, I use the dx and the dy to represent the total due of MRT, okay? Dy, total due of MRT. Okay? So I give some notation like this is alpha, this is beta, and this is tau, this is phi, and this is phi. And the tautological line bundle I use Kasi, okay, Kasi here, and I use eta to represent the tautological line bundle of Pty, and this is eta tilde, okay? So this is the basic notion. Okay. So the first thing is you can see dx is numerical equivalent to axc minus b tau pullback hx. So this hx is some ample divisor. And for a positive. Okay. So the first thing is because this x is pk number 1, then this ptx is pk number 2. Okay? So for ptx pk number 2, how many divisors we can find? So first of all, we can find the pullback of the ample divisor. So this is one divisor. The second divisor is the tautological line bundle is another divisor. And finally, we have the total due of MRT, which is also a divisor. Okay? So for these three divisors, we can always write in some numerical equivalence. Okay? Or linear equivalence because it's rationally connected. And then surely this A is positive. Why? Because if you take a fiber of this projection, then by projection formula, this is vanishing. Okay, and the dx dominates the base. Dx dominates x. So if you intersecting with this dx with a fiber, then it has positive intersection. So that, and then also this Kasi times this fiber is always 1. Okay, so this A has to be positive. And the second thing is B is positive if and only if Kasi is big. Okay, so this is due to Baohua Fu and Jie Liu in 2002, or another joint paper of Anna Hell's Huring, Jie Liu and Feng Shao in 2002. Okay, so it tells us that if the tangent bundle is big, then this B is positive. You can imagine that this is an extremal divisor. This is also an extremal divisor, and if this Kasi is big, then it lies in the interior of the pseudo-effective cone, and the pseudo-effective cone has two generators. One is dx, the total due of MRT. The other one is the pullback of hx. Okay, so this B is positive if and only if Kasi is big. But actually, it is more involved, but I skipped the details here. And then also note that there is another very important property. So this dx is covered by. So let us recall what's the definition of total due of MRT. The total due of MRT is covered by the minimal section, right? And what's this minimal section? So it covers by L bar such that this Kasi times L bar is 0. Okay? Because this is from the definition of the trivial quotient. so that this dx itself is covered by those L bar such that it has zero intersection with c. So by using this, the first point and the second point, you can obtain that this dx is covered by L bar with dx times L bar negative. Why? Because if you intersecting both sides with the minimal section L bar, you obtain this c times L bar is 0. And this L bar does not contract along the projection because it's the minimal section. So that this hx has the positive intersection with this, the image of this L bar. Okay, this is positive, but you minus b, so it's negative. So this means dx is covered by those L bar such that it has negative intersection with dx. Okay, so what does it mean? It means the restriction of dx to itself is not pseudo-effective. Okay, so we consider this, we define this dx prime to be the proper transform of this dx. Okay, so lives in f pullback ty. Okay, so for this dx living here, we consider its proper transform to the f pullback ty, this stage. Okay, we consider this alpha inverse and the beta image. Okay, we define it as the dx prime. Okay, so this lives in the P f pullback ty. Okay, so this is just the alpha inverse and the beta image. Okay, so we prove dx prime actually is equal to f tilde pullback dy. So if we prove this, then this means while this rational map, this dx is sent to dy. This dx is sent to dy. Then we conclude by theorem C. Okay? So what we would like to prove is this dx prime actually is the pullback of dy. But why is it? Let me see how many minutes I left. Okay, 10 minutes. I think it's okay for me to prove this. So we have this 0 to tx to f pullback ty. Okay, as I just explained, we have this injection. So we have the global, we have the injection of the global sections. Okay. It's just take the symmetric power and the tensor product with some line bundle, and then you get the induced injection. So we're using this property. Okay, then we can obtain that there exists some non-negative integer m such that this a eta tilde minus b phi pullback hx, this actually is a linear equivalent to dx prime plus m phi pullback hx. Okay, so using this injection and also this property, you can deduce this. You can find some non-negative integer m, so that this a eta tilde minus b phi pullback hx is linear equivalent to dx prime plus m phi pullback hx. I will skip the details, but this is very easy to check using this injection. If you have any problems, we can discuss later. Okay, now we are almost till the end of the proof. Oh, sorry. Okay. So now we obtain this dx prime is linear equivalent to a eta tilde minus b plus m phi pullback hx. And then we obtain this dx prime is times this c bar prime is negative. Why is it? Because, as I just explained, except for this dx, we have also dy. And dy is also covered by rational minimal section C bar, which has negative intersection with it. Okay? So if we consider this, so this C bar living in this PTY, and we take any pre-image C bar prime here. Okay? We take any pre-image C bar prime here. And then clearly this eta tilde times this C bar prime is equal to 0, because it's just from the projection formula. Because this C bar is coming from the downstairs. Okay? But this is positive. I mean, the HX has positive intersection with C, so that this is negative. Okay? So this is negative means dx prime times C bar prime is negative. So this means dx prime. Okay, so this means this f tilde pullback dy. Note that this is covered by curves C bar prime, such that eta tilde times C bar prime is equal to 0. Then you can see this f tilde pullback dy coincides with dx prime, because this means this C bar prime is contained in dx prime. Because a variety has negative intersection, a divisor has negative intersection with a curve. So this means this curve has to live in this divisor. Okay. Okay. So I'm sorry for this. How many? Oh, I still have some minutes. Good. Okay. So now I give a very, maybe very, how to say, troublesome proof here. I'm sorry for the confusion caused, and if you are interested in this topic, I'm very happy to discuss with you, because there are too many notions, and actually the theory itself is very deep. So I'm sorry to give this maybe not very good experience to understand this situation. But I hope that you could be interested in this topic after my talk. So finally, I will give some applications. The application is more easily, okay. So I will give some applications. So the application is, I just give one application. It's a very clean application. So every nonlinear complete intersection of dimension greater than or equal to 3 admits no surjective endomorphism of degree greater than or equal to 2. Okay. Okay. So why is it? Why is it? Because as I said, suppose there is such a non-isomorphic surjective endomorphism, then as in our proof, actually we show this tangent bundle is pseudo-effective. Okay, although in this proof, in this part, I didn't give more details herein, but if you remember correctly, in our theorem B, I showed if it exists a non-isomorphic surjective endomorphism, then it has pseudo-effective tangent bundle. But for we can in the joint work with Feng Shao, we proved that this nonlinear complete intersection is actually its tangent bundle can never be pseudo-effective. Okay, can never be pseudo-effective, so that it admits no non-isomorphic surjective endomorphism. Okay, and another thing is, I want to ask an open question. So now, let me summarize the situation. So given a non-isomorphic surjective endomorphism, degree f greater than or equal to 2, we obtain some pseudo-effectivity. Okay, we obtain some pseudo-effectivity, and if we further assume some bigness, then plus some some other assumption, some mild assumption, we obtain this conjecture. So the question is, how to reach this bigness from the pseudo-effectiveness.
Sorry, and all these assumptions in the corollary, and here you need to check that it's not do the assumption.
Yes, because for the completing section, it's total, it's a dual, it's how to say? For completing section, it's VMRT is also a completing section. And then, as I said, for completing section, nonlinear completing section, in the it is always non-dual defective, so that all of the these assumptions are automatically satisfied in this situation. Yes. And also note that so from the pseudo effectiveness to the bigness is still a big there is still a big gap, but so the first step I expect is whether just one more minute. Just one more minute. Can we prove the non-vanishing? Okay, under the dynamical assumption. Because under the dynamical assumption, we proved that this Tx is pseudo-effective. So this means after you add a little bit ample, then it has many sections. It has to be big. But what if this symmetrical M of Tx itself is now, whether this is, how to say, whether it is vanishing or not. So because this Tx itself is pseudo-effective, if you consider the cone, of this pseudo-effective cone of this Ptx, then once this Tx is not big, if Tx is big, then this is what we would like to see. So if this Tx is not big but pseudo-effective, then it lies in the boundary of this pseudo-effective cone. Okay, this tautological line boundary lies in the boundary. And because this is Picard number 2, so the cone is quite easy to understand. So this problem reduced to, for Picard number 2, this smooth rationally connected projective variety, whether its pseudo-effective boundary admits a section. Okay, so this is our question. So if this is, it has a positive answer, then I think this is a big through towards this red part. Okay. Okay. Okay, so I think I will stop here. I'm sorry for this today's talk, but tomorrow it's more birational geometry. Yeah, it's more easy because we are only working on dimension 3. But this is actually is for arbitrary dimensions, so the explanation is not very easy to present. But I believe tomorrow it's more easy to understand, and it's surely independent of today's talk. Okay. Okay, thank you.
Any questions? In this case, let's thank Wally again and recall that
Thank you.
We have a coffee break, which is open for discussions.
Okay.